Hello, welcome to my tutorial about Bob's Biometric Recognition Framework. I am Manuel Ganter, and I have been working at EDAP, at the EDAP Research Institute for a while, where the Bob framework was programmed. And I'm currently working in the Vision and Security Technology Lab in the University of Colorado Springs. Okay. So what we will learn today, one thing, so if you haven't installed the tutorial yet, or the software that is required for the tutorial yet, it is here available, which is also linked on the IJCB webpage. And the whole talk, the PDF slides are also available there. And it might be a good idea to download them, because you might want to look forth and back when we are actually in the hands-on sections. Okay, so we will talk about 5 different things today. So 5 topics. The first topic is about general biometric recognition, so which steps are required for this. Then we will start with a small hands-on session on using the biometric framework bob.bio. And then we will see a little bit of Gaussian mixture models and how they are used in the framework. And finally, the probably most interesting part will be how to implement your own biometric recognition algorithm, how to extend the framework so that it fits to your needs. And the last one is how to provide reproducible research, which is what the whole framework is about. Okay, yeah, these are the 5 topics. Before we start, I want to advertise a special issue that I agreed to be the guest editor of. It's in the Journal of Imaging, and the special issue is about face recognition, automatic face recognition, with a focus on open set face recognition, but not necessarily. So you're invited to submit papers there, of course. And the URL is given down here. Okay. Yeah, so one note, whenever in my presentation I have something in green, this means that the link that you can actually click on. Okay. All right. So let's start with the general biometric recognition. And we will see a little bit of what are applications of biometric recognition, which tools or which steps are taken in biometric recognition toolchain, and how to evaluate a biometric system. The goal of a biometric recognition is to generate a score for a pair of images or a pair of samples in general. So given one sample in the gallery, we want to get high similarities to the same identity. So, and if you don't recognize, that's all me. And you want to produce low similarity scores to other people. So this is Terry, and this is my old boss, Sebastian Marcel from the EDAP Research Institute. How do you want to use them? So there are several applications. For example, you can, nowadays, you have it on your phone, so you can just take the phone in front of your face and get the phone unlocked. So that's an authentication. Then there is a verification, which means that you have a badge or an ID card where your biometric samples are stored, and you want to go through, for example, border control, and they take a fresh sample and compare it with whatever is stored on your ID card. Then we have the identification, where we have a larger list of people that you know, and you have an image of someone, and you want to see who is it. And then the final one, and the most difficult one, is the watch list, where you have a list of unwanted persons, and you have let's say, a surveillance camera, and you want to find out whenever someone from these unwanted persons is going through your images. There are also more biometric recognition applications. For example, an image search. So you have a set of images and you want to retrieve all the images that contains a certain person. There is the face clustering. Again, you have a group of images and you want to see which persons are in the image, so group them together. And the final one is forensics, where you have an image of a suspect, and the suspect, you want to find this suspect in a surveillance camera image, for example. Okay, let's go a little bit deeper in how authentication and verification and all these works. Authentication and verification are actually basically the same thing. It is a one-to-one comparison, so you have one image, one sample that you have stored on an ID card or something, and you have one sample that is taken from your, a live sample that is taken. And so for this, generally you enroll a model. So this is what you have stored on your ID card or on your phone. And then you take one or several probe samples and try to compute the similarity between the model that you have stored and the probe. And finally, you have to threshold this similarity in order to either accept it when the score is above threshold, or reject it so that it's not the same person when it's below threshold. Usually in these scenarios, you have a controlled environment, so you are taking the original sample in a controlled environment. You are taking the probe sample in in a controlled environment, and the subjects cooperate with the system. So this is a very simple task, and for face recognition, for example, it's considered to be solved since a couple of years. Then we have the identification, which is a little bit different, because you have several images or several models of different so-called clients, subjects, in a gallery. And when you have the probe image, you have to compute the similarity between all the models in your gallery and the probe. And you have to return one or several of the most similar clients, usually to a human operator, who will then check if it's one of these. And there are two variations of that. One is the closed set identification, where you guarantee that the probe always has a match in the gallery. That's, again, the simple case. And there's the open set identification, where the probe might not actually be in the gallery. So, and this is very difficult because you will need a score that is low for everyone in the gallery. And so that is below threshold for everyone in the gallery. And finally, we have the watch list scenario, which is an M-to-N identification. Again, you have a list of clients that you have in your watch list, but instead of just providing a probe directly as a face, and you know that it's a face, you have to detect all the probes in a given sample, which means that you might actually have something that is not a real face, for example. And then you compute the similarities between all the models and all the probes and decide which of the subjects or of the probes are actually on your watch list. So that's more or less the scenario of surveillance camera and a watch list. So you have a list of criminals that you want to detect. And the problem with that is that it's usually you have uncontrolled samples and you have uncooperative subjects, sometimes even trying to hide themselves. You have many more unknown than known subjects. And as I said, this your algorithm must be able to handle the false alarms of the detector. Okay. Now, the biometric recognition is actually a little bit of a 5-step process, at least how it's implemented in the Biometric Recognition Framework. You have a database that actually provides the data, the raw data, to the system. And it also assures that, so that when you compare two different algorithms, that the results are actually comparable. Then you have a pre-processing step, which detects the samples, the biometric signals inside the raw data. And you have an alignment step, you have an enhancement step, so that you can actually increase the raw data, so improve the raw data so that it can be recognized easier. Then usually you have a feature extraction step, and then you have some face or biometric recognition algorithms which perform the model enrollment and the scoring. And finally, you have from the database, you have a set of list of comparisons of the same identity and different identities. And this goes into the evaluation. Okay, let's have a slightly deeper look into that. So the data set, the database, as I said, it provides the data, but not only the raw data, but it also has some annotations. For example, in a voice signal, where the voice actually starts, where the voice ends. In a face recognition system, maybe it is the locations of the eyes, something like that. And what is also important is that it provides an evaluation protocol. So for each data set, you have a list of images or samples that are actually used to train your system. And then the data set defines what is the enrollment data, so which samples should you use for enrollment, which is your probe data that you test your enrolled data with, and sometimes there's also some score normalization set that is defined by the protocol. Generally, there are two different types of protocols. One is the protocol where you have a training and a test set, which might be biased or unbiased. A biased training set or a biased data set is when you have the same identities in the training and in the test set. An unbiased protocol, you have separated identities in the training set, and you test your algorithm on different identities. And then there is the so-called Lausanne protocol, which splits the data further. So it has a training set, it has a development set, and an evaluation set. And all the three have disjoint identities. And the development set is actually used for optimizing the parameters of your algorithm. And you only calculate the results on the test set after you have chosen all the good parameters of your algorithm on the development set. Okay, the pre-processing step looks like this. For example, for the face, in the pre-processing you have a face alignment step. So in the first place you get a face detector which detects a bounding box, like this red bounding box here. Then inside this bounding box you might want to detect some landmarks. Sometimes you can use an algorithm that detects both at the same time. And you can use these landmarks to either the face detector, the result of the face detector, directly to crop the face, or you might want to use the automatically detected landmarks to align the face. Sometimes the data set also provides hand-labeled annotations, so you can use the hand-labeled annotations and so on. And then there is some enhancement, in this case photometric enhancement, where you can get different types of enhancements of the image. For example, you just extract the color, so that's without any enhancement. You turn it into grayscale. You have an histogram equalization. You have a self-quotient image, which was actually developed here in the Colorado, no, the University of Colorado, CSU. It's Colorado State University. Okay, yes. And then you can have other pre-processing algorithms, like there is a famous Chan-Triggs algorithm, or you can extract local binary patterns as pre-processing, for example. And then, okay, we have these pre-processed images. Now we extract some features or pre-processed samples. One very simple extraction technique is just concatenate all the output of the previous step into one long vector and take that as your feature. So that was one of the first ways how to do biometric recognition, especially face recognition. There are other types of global features, for example, local binary pattern histogram sequences, where you extract a local binary pattern per image and then extract it into a local histogram and concatenate local histograms to finally get your global feature. There are neural networks nowadays, so you just have a pre-trained network, you give your data to the input layer, and at the output layer you extract your features. And so these were the global features, and then you also have local features. For example, you have Gabo jets, as an example, that you extract at local positions in the face. Or you have DCT block features, so where you separate the face into small blocks and compute the DCT on each of the blocks. Just keep the highest values, the highest DCTs, and then concatenate or get a lot of features for the same face. And you're actually not concatenating them in this case. You just keep them as different observations, and we will use them later. But local features are obviously not only for the face, but you can also have speech signals. So this MFCC features for speech is, for example, a local feature. And for fingerprint recognition, you can also have local features like the minutiae that you extracted several places in the image. Okay. Now we have another step, which is the feature projection step. That's an optional step. For example, one very traditional feature projection is using PCA, principal component analysis, which computes a linear subspace of your data. And given a data set, given the training set of your data set, you can actually train this projection matrix, and then for recognition, you just use this to extract features from the gallery or probe samples. And yeah, so there are two different traditional techniques. One is the eigenfaces that you can get from the PCA, from the principal component analysis, or there's the so-called Fisher faces, where you do a principal component analysis and afterwards local discriminant analysis, and this is the joint projection matrix of that, which you can visualize actually as faces. Okay, now model enrollment. The idea of the model enrollment is that given one or more samples from the same person, you want to combine them into a representation of the person. So, and this is a little bit, so there are different kinds of solutions for that. There are simple solutions which says, okay, I have 5 images of this person. I want to enroll that into a model So the model just stores all these 5 features. Or it computes the average of these 5 features, which is also which is getting more attention right now, because that works very well with deep features. But there are also more complex solutions. For example, you train a support vector machine or another classifier to be able to separate the samples of your model from the training set samples, so that you can say, okay, when you get another feature, then you can just say, okay, on which side of this of the support of the SVM classifier it is it the same or a different person? And you can do.
Do you do that per subject, or is it for a gallery?
So usually you do that per subject, because in most cases it is not allowed by the protocol that you use other identities to enroll a model. So what you can do is you can compute an SVM to the training set. So with the training set at the negative samples.
So the training set for the SVM will contain n number of images for one subject.
Yes.
So if I had like m subjects in my gallery,
Mm-hmm.
I have m trained SVM models.
Yes, in this case, yes.
In this case, and then okay.
Mm-hmm. So because the idea is really that you should not have, so when you want to add another model into your gallery, then you should not rely on the other models in your gallery. So you don't want to retrain all the other models in your gallery either.
And then when we're doing when you get a new probe image,
Mm-hmm.
and so the new probe image, you pass it through all these 100 models, and those models are going to give us the similarity score.
Yes.
And in that, the highest one you hope is going to be the person.
That's identification, yes.
Yes.
Yeah, so, okay. And another complex solution, which we will see later a little bit in more detail, is the so-called maximum a posteriori adaptation, which is used in Gaussian mixture models. Okay, and the scoring happens like that. You have one model and one probe feature, and you want to compute a score for that. And there are different ways to do that. There's also depending on the type of feature that you have extracted, if you did a feature projection or something, how you did the enrollment. So that's a little bit dependent on your algorithm. The most simple ones are simple feature comparisons, where you use a similarity function like a cosine similarity or histogram similarity in case you had extracted histograms, or Garbo-Jet similarity in case you had extracted Garbo-Jets, and so on. There are more complex solutions like the SVM that we have talked about, where you get the probe feature, classify it with your SVM, and depending on where it is, on which side, you get a positive or a negative score. And something that we will see later on is the log likelihood computation for the Gaussian mixture model. And there is one variation of that, which is when you have several probe samples and so the protocol provides several probe samples for one comparison, then you have to see what to do with that, how to join these several probe samples into one comparison. So usually what is done, you compute the similarity from all probe samples to your model and take the maximum similarity or an average similarity or something like that. But there are also more complex solutions to that. And finally, we have the evaluation step. And in the evaluation, depending on what you want to evaluate, given a set of these scores, you can do basically any type of evaluation that you want. For a closed set identification, usually you get cumulative match characteristics or rank R recognition rates. So the rank R recognition rate says, okay, I have several probes. I have, for each probe, I know in which rank my gallery is, which means that how many samples from the gallery are more similar than the correct identity from the gallery. So this is how the recognition rate is computed, and the cumulative match characteristics curve, CMC curve. It just cumulates the recognition rate over several ranks. So here, for example, at rank 10, you plot the probability, or the probability that your probe sample is at least recognized, or it's within the best 10 matches. Then we have open set identification, which evaluates like the watch list scenario. And the difference here is that you have some probe samples where you know that they are not in the gallery, and some probe samples where you know that they are in the gallery. And you compute the so-called detection and identification rate based on a given threshold, and the so-called false alarm rate based on a given threshold. And you, in the detection and identification rate curve, you plot the DIR over the FAR. What is very important here is that when you have an unknown probe, then the similarity between all models and probes must be below threshold. So if you have one of the similarities to any of the gallery is above threshold, then this counts as a false alarm. And here also, when you have a misdetection of your detector, then this also counts into the false alarm rate if it's above threshold. And then we have the verification of, and in the verification, you usually compute also two rates based on a threshold, which is a false non-match rate and a false match rate, also known as the false acceptance rate and the false rejection rate. And for the false non-match rate, you base your you compute a threshold, and then you only look at the scores that were matching genuine scores, where the gallery and the probe are actually from the same identity. And you compute the number of samples where the score is below threshold, so that the error rate when it's below threshold. With the false match rate, you do that on the impostor scores, so which means that these scores were generated between a gallery and a probe of different identities, and you count the number of scores that are actually above this threshold. And then you can plot the false match rate and the false non-match rate. So this is actually 1 minus the false non-match rate in the receiver operating characteristics score curve, ROC, or in a detection error trade-off curve, DET, which basically plot the same information, just a little bit different, with different axes. And finally, when your data set contained the Lausanne protocol, one relatively new measure is the expected performance curve, where you compute your threshold based on a given, So you take the scores, the false match rate and the false non-match rate of your development set, and compute a threshold by minimizing that where alpha, so where you slide between the false match rate and the false non-match rate. So a high false match rate and a high false non-match rate. And then you take this threshold and you compute the so-called half total error rate, which is the average of the false match rate and the false non-match rate on the evaluation set, and you plot that for different values of alpha, so that you can see where so you can check an operating point where you want to set your threshold. Okay.